The Sumitomo 6,500-ton hot forging press is a high-capacity, precision-engineered system designed for the production of large and complex crankshafts used in heavy-duty applications such as marine engines, locomotives, and power generation equipment. This mechanical forging press applies up to 6,500 tons of force, enabling it to shape massive steel billets at elevated temperatures with high accuracy and repeatability. The hot forging process begins by heating the billet to a temperature range of approximately 1,200 to 1,250 degrees Celsius, ensuring optimal material flow and workability. The press is equipped with automated billet handling systems, precision die alignment mechanisms, and real-time process monitoring controls. Forging operations are typically completed in a multi-step sequence, which may include preforming, blocking, and final forging stages, each optimized for grain flow alignment and internal structure refinement. The closed die configuration enhances dimensional consistency and structural integrity, producing crankshafts that meet strict tolerance and fatigue resistance requirements. Post-forging operations such as flash trimming, heat treatment, and ultrasonic inspection are integrated into the production line to ensure quality control. The 6500T press significantly improves forging efficiency, product reliability, and production throughput, while maintaining the mechanical properties essential for high-performance crankshaft applications. The forging of a tubular billet is carried out using a 4-die forging block in combination with 2 forging manipulators. This setup ensures symmetrical and uniform deformation of the billet, enhancing both dimensional accuracy and material integrity. The manipulators synchronize to hold and position the billet precisely, allowing controlled axial movement and rotation during each forging stroke. This precision is critical for producing thick-walled pipes where structural uniformity is essential. The 4-die system minimizes internal stresses and ensures high strength in the final product, meeting stringent industry specifications for mechanical performance and reliability. The production of iron rods by Aseros de Guatemala begins with the transformation of scrap metal into steel billets, forming the raw material for rolling. Scrap is first processed through a shredder and magnetic separator to remove impurities and increase density. It is then melted at 1,600 degrees Celsius in an electric arc furnace and cast via a continuous casting machine into 12-meter-long billets. These billets are either transported hot to the rolling mill or stored for cold charging. Using 2 hydraulic cylinders, billets are fed into a furnace that reaches 1,150 degrees Celsius with a capacity for 118 billets and a heating cycle of 3.5 hours. The heated billet proceeds to the roughing mill, where it undergoes the first 7 of 19 rolling stands. These reductions are critical, with material deformations reaching up to 25% per pass. The steel is then formed into ribbed iron rods during the 2nd and 3rd rolling stages, with the tri-slitting process enabling up to 3 rods to be produced simultaneously. After natural cooling, rods are cut to standard lengths 6, 9, 12, 15 meters, bundled, inspected, and labeled under international quality standards before distribution. The production process of Jones-Way plier tools involves multiple precise stages to ensure superior quality. Initially, raw materials undergo forging to form the basic components. These components are then subjected to lathing for dimensional accuracy. Following this, heat treatment enhances the hardness and durability of the metal. Surface treatment is applied to provide corrosion resistance and improve aesthetics. Afterward, the parts are assembled with precision to ensure optimal functionality of the movable joints and jaws. Finally, rigorous testing, including metal microstructure examination, confirms product reliability and performance. This systematic process guarantees the high standard of Johnsway tools across all variants. The SMS Group's hot rolling process at the Baotou rail mill in China is a comprehensive and highly controlled production system. The process starts with heating steel billets to around 1,250 degrees Celsius in a walking beam reheating furnace, ensuring uniform temperature distribution for optimal metal flow during rolling. After heating, billets undergo high-pressure descaling at 250 bar to eliminate surface scale and impurities, which could otherwise affect the quality of the final product. Following descaling, the billets pass through the roughing mill stands, including the first and second breakdown mills. These stands have large diameter rolls and perform multiple reversing passes, progressively reducing the billet's thickness while maintaining dimensional accuracy. Special tilters carefully flip the billets to ensure even deformation and prevent defects. The roughing phase prepares the material for the finishing train. The finishing train is equipped with SMS's Compact Cartridge Stand (CCS) technology, which provides exceptional rigidity and precision needed for high-speed rail profiles. The system includes hydraulic roll adjustments and automatic gauge control (AGC), enabling rolling speeds of up to 8 meters per second while maintaining tight tolerances and excellent surface finish. After rolling, rails are stamped with unique identification numbers for full traceability and undergo cooling on walking beam beds, where they are carefully cambered and straightened using both horizontal and vertical straightening machines. These machines feature individually driven rollers to precisely control straightness and relieve internal stresses. The rails then pass through a dedicated test center, where thorough inspections are conducted using the latest techniques to ensure compliance with international quality standards. Finally, the rails are cut to length, loaded and prepared for shipment. The plant's flexible design also allows production of other steel sections, such as beams and profiles, enhancing operational versatility. The spring manufacturing process begins with heating spring steel wire to nearly 1,000 degrees Celsius in a walking beam gas furnace. The heated wire is then shaped on a CNC-controlled coiling machine to ensure consistent spring formation. After coiling, springs are quenched in circulating oil to harden and prevent surface hotspots. Next, the springs enter a tempering furnace at over 400 degrees Celsius for about 20 minutes, enhancing elasticity and reducing brittleness. Optional end grinding is done automatically, followed by shot peening to relieve surface stress and improve durability. Finally, springs are scragged, load height tested, powder coated, labeled, and boxed for distribution. The process starts with a square billet that is forged into a round shape. A central hole is then drilled to prepare the piece for further forming. The part is mounted on a large rotary forging machine, where it is gradually expanded in diameter while being shaped into a large ring resembling a tire. This rotary forming process ensures uniform wall thickness and precise geometry. After forming, the component undergoes rough and finish machining to achieve the required dimensions and tolerances. Finally, the surface is ground to a smooth finish, ensuring durability, structural integrity, and optimal performance in high-load rotary kiln applications. The production of high-pressure gas cylinders at Vitkovi cylinders begins with a chrome-molybdenum steel billet, which serves as the raw material. The billet is first heated to a precise temperature in an electric induction furnace before being transferred to a powerful extrusion press. There, it is transformed into a thick-walled hollow form known as a pot. This semi-finished cylinder is then elongated to its final length using a horizontal press. A neck-forming machine shapes the top of the cylinder, completing its external profile. Each cylinder undergoes annealing heat treatment to achieve the required mechanical properties. Rigorous testing follows, including ultrasonic inspection, strength verification, and pressure resistance testing. Surface preparation is the final step, where the cylinders are painted in accordance with industry standards and customer specifications. Once labeled and approved, the finished cylinders are packed and shipped globally, ensuring safe and reliable performance in high-pressure gas applications. The 12,500-ton hot forging press line for front axle beams begins with billet heating to the required forging temperature. The heated billet is then subjected to reduced rolling, which refines its grain structure and prepares it for shaping. Next, the billet is bent in a preforming die to roughly match the desired profile. It is then positioned in a blocker die cavity where its shape is further refined. Finally, the part undergoes precision finish forging in a closed die and is trimmed to remove flash and excess material. This multi-stage process ensures high-strength, dimensionally accurate front axle beams. The Clinton bar mill supplies hot-rolled bars with sound center integrity, ranging from 6 inches to 16 inches in diameter and up to 40 feet in length. Larger bars are produced using open die presses. Each tartan bar undergoes a preliminary forging stage to consolidate the core, followed by repeated planishing passes through rollers to achieve a consistent rolled surface. This process ensures a minimum center reduction ratio of 3:1. Bars can also be peeled or machined to meet customer specifications. Optimized roll sizes reduce excess stock, while efficient production scheduling ensures consistently short lead times. The manufacturing of concrete pressure pipes involves 4 main types: C300, C301, C302, and C303. Each utilizing combinations of steel, concrete, and mortar. C300 starts with steel sheets welded into a cylinder, fitted with joint rings, hydrostatically tested, then wrapped in steel cages before concrete is placed and steam cured. C301 follows a similar beginning but adds pre-stressing wire wrapped under tension and cement slurry for enhanced strength. C302 omits the steel cylinder and relies on concentric steel cages embedded in concrete between inner and outer forms. C303 uses a steel cylinder with mortar lining, wrapped in mild steel bar and coated with additional mortar. All types undergo curing and quality checks before shipment, offering robust, durable solutions for pressurized water systems. Submerged arc welding, SAW, is applied to join thick-walled components like a 60mm cone or concentric reducer. The UP process ensures deep penetration and high weld quality by feeding flux and electrode automatically, producing clean, uniform welds ideal for heavy-duty industrial applications. Perfiles AG, manufactured by Aseros de Guatemala, begins with scrap reception at its Masagua industrial plant, Central America's largest steel production site. Scrap is cleaned, densified, and magnetically separated, then melted at 1,600 degrees Celsius and cast into billets via continuous casting. These 6-meter-long billets are reheated to 1,150 degrees Celsius, rolled through 20 mills to shape profiles like angles and channels, then cooled, straightened, and cut to precise 6-meter lengths. Each bundle is magnetically grouped, strapped, labeled, and stored for shipment. Strict quality control ensures compliance with international standards before final distribution to customers. Schmiedewerke Groditz GmbH operates an electric arc furnace producing up to 50 tons of liquid steel per heat, using 100% sorted scrap meeting strict quality requirements. The furnace tap-to-tap cycle lasts about 2.5 hours. After tapping, the molten steel undergoes alloy refinement and purity purging in the ladle furnace, followed by vacuum degassing in VDVOD equipment. The steel ingots, optimized for subsequent forging weight and size, are typically square or rectangular for tall steels. An optional electroslag remelting process enhances purity and homogeneity before forging. Ingots are transported at about 700 degrees Celsius, reheated to 1,200 degrees Celsius, then forged on a 60 meganewtons press with precision tooling and computer control. Post-forging heat treatment in advanced bogey hearth furnaces ensures hardness consistency, verified by automated hardness testing and ultrasonic inspection and shipment to customers. Stainless steel looks shiny and new even when made from recycled scrap. The process starts by collecting scrap metal like old sinks and pots, which are melted in an electric furnace. Nickel and chromium are added to increase strength and protect against corrosion. The mixture is heated with powerful electric arcs until it boils, producing bright sparks like fireworks. After melting, the steel is refined by blowing argon and oxygen gases to remove impurities, which form slag and are discarded. Metallurgists carefully control temperature and chemical reactions throughout. The clean molten steel is poured into molds to form slabs or billets, then reheated to soften for rolling. Hot rolling stretches and thins the steel using water-cooled rollers, sometimes creating strips up to 600 meters long. The strips are cooled and coiled. Next, the steel is cleaned with hot acid to remove rust and scale, then annealed, heated, and slowly cooled to relieve stresses and soften it. Cold rolling follows to finalize thickness and surface quality, making the steel smooth and shiny. A thin chromium oxide layer forms naturally, protecting the steel from rust. Finally, sheets are cut to size and ready for use in many products. The manufacturing process of a bronze bushing starts with heating the bronze material to a high temperature, around 600 degrees Celsius, to make it malleable. The heated bronze is then shaped carefully to the required dimensions. During the process, precision is crucial. especially when drilling or adjusting holes to fit specifications. Workers ensure that metal parts are handled safely and measured accurately to avoid mistakes. The bushing is inspected continuously for weight and size to meet standards. Once shaped and drilled, the bronze part is cooled and prepared for finishing. Throughout the process, experienced operators use tools and machines to achieve the perfect fit and quality for the final bronze bushing product. The flange manufacturing process starts by heating the steel billet to a high temperature to make it malleable. Once heated, the billet is forged into the initial shape using a press. The inner diameter is then expanded to the required size using CNC tools. This forming process is repeated for different dimensions depending on the flange specifications. After forging, the workpiece is left to cool gradually in controlled conditions to relieve internal stresses. Finally, quality control is carried out using advanced measuring machines to inspect dimensional accuracy, surface quality, and structural integrity before the flange is approved for use.